So let's take a look at number 27. Let's find the determinant for this. So we've got a couple of different options in terms of expansion. Now notice this is a 4 by 4, which means there is no shortcut. So we have to do this the long way with expansion. Now if we expand along the first row, we could make our work a little bit shorter because we have a 0 here, and we know a 0 times a cofactor would end up being 0. Or we could expand along the third or the fourth rows and have the same result. But if we were to expand along the first column, we have 2 zeros. So that's going to cut our work even more than just having 1 zeros. So that's the way I'm going to work this one. Now, it doesn't matter. You can choose to expand along any row or any column. You're going to get the same result in the end. I'm just going to choose to go along that first column to cut some of the work. So if we were to expand along that first column, so we're going to have 5 times negative 1, and that's going to be to the 1 plus 1, first row, first column. That's where the 5 is. And if I take out the 5, that column and that row, I'm left with a 3 by 3. So this is going to require some fun skills here. So our next setup, we've gone along that first row. Now we need to go through that second row. So notice that row and column intersect at 4 times the negative 1. That's in the second row, first column. And then that minor is 306, 2 negative 3 4, and 1 negative 2 2. And I'll show you the setup again. If we go along that third row, notice we're going to have a 0 in there. This is in the third row, first column. Here's your minor. But once again, 0 times anything is 0, so that guy's going to go away. But I'm writing it out so you can see what it would look like. And then along that fourth row, so we're taking out that first row, fourth column. And the minor. Is that. And once again, 0 times anything is 0, so we really are only going to have to compute the determinants of these two 3 by 3s to get to our final answer. So I'm going to simplify. So this is going to be 5. Negative 1 squared is a positive 1. 1 times 5 is 5. Times this determinant. And we're going to do some side work to find these determinants. Then we're going to have 4 times negative 1 cubed. Negative 1 cubed is a negative 1. Negative 1 times positive 4 is a negative 4. And then we're going to have to find that determinant. So we're going to go off to the side and we're going to find those determinants. So here's my side scrap work. So I'm going to start with that first one. 6, 4, 12, 2, negative 3, 4, 1, negative 2, 2. And I am going to use that shortcut method, which is where I can recopy the first 2 columns. And I can multiply down the diagonals. So that's going to be negative 36. Just be careful that everything lines up. It's easy to write sloppy and add or multiply the wrong things. And then 12 times 2 times negative 2 is negative 48. Minus. Go back down this way. 16. Negative 48. 12 times negative 3 times 1 is negative 36. So And there's negative 68 minus negative 68, which is 0. So this is 5 times 0 minus 4 times something. Now let's figure out what that something is. So this is the determinant of that second 3 by 3. And I'm going to use that shortcut method again. I like that for 3 by 3s. Just makes life a little bit easier. So we're going to multiply. Zero. Subtract, then multiply the other way. And that's going to be 0. So this determinant is 0. And what this means is that this matrix actually does not have an inverse. So the determinant's used to tell us things about the matrix. Instead of having to go through all those row operations and then discover, oh wait, I can never get the identity on the left if I were to try to do these row operations. If you can never get the identity on the left, then you will never get a inverse on the right. So that one's kind of fun. So, and all 4x4s are going to work the same way. It just really depends on how you see to do it. I saw going down that first column, we could have went along that first row if we wanted to. We could go along any row. But as you saw, going down that first column had some benefits because of the zeros in that column. That gave us a little less work to do. If we would have gone along the first row, we would have had to compute the determinant of 3 by 3 matrices instead of just 2 3 by 3 matrices. So now that we've talked about that, let's go on to talk about determinants of triangular matrices. So it turns out that if we have a triangular matrix, and this would apply for matrices that are diagonal as well. It's a special case of triangular. So if we have a triangular matrix, then the determinant actually ends up being the product of the entries down the main diagonal. And I want to show you why. So let's just talk about a 3 by 3. And I'm going to use a lower triangular matrix. It doesn't matter. The process would be the same for an upper triangular matrix. So it would make sense for us to expand along the first row, or we could go down that last column, just because we've got zeros in here. So suppose we were to do that and expand along that first column. I'm just kidding, first row. Suppose we were to expand along that first row. So what would the setup look like? So it would be A11 times the determinant, A220, A32, A33. And then it would be plus. Now we're going down that second row. You see how that's going to be a 0. Oops. Don't forget the negative 1 there to a power. And then we would have 0 times negative 1 to the 1 plus 2 times the cofactor. And then we would have 0 times negative 1 to the 1 plus 3. Once we move to that third column, That's where they cross. And then we would be left with this minor. But 0 times anything is 0. We know that, so those are gone. So really, this determinant really just boils down to this guy. What is that? Well, this is going to be a11 times 1 squared, which is positive 1, times the determinant of a22, 0, a32, a33. And that determinant would be a22, a33 minus 0. So the determinant is just a11 times a22 times a33, which are the entries down that main diagonal. If we were to go back and look at what A looked like, there are the entries down the main diagonal. So you can see how it's going to be that product. So that's for a lower. Uppers work the same way. So if we had an n by n matrix, and this is again a lower triangular matrix because the entries are either the non-zero entries are either on the main diagonal or below the main diagonal. So the determinant of that matrix, I'm going to call it matrix A. It would be a11 times negative 1 to the 1 plus 1. And if we were to take that out, then we would have this guy left. So a22, 0, a32, a33, an2, an3 to ann. And then we would have plus 0 times some stuff, plus 0 times some stuff. But since 0 times anything is 0, it's unnecessary to show that. So then we would have a11 times negative 1 squared, which would be a positive 1. So this is just going to be a11 times this determinant. And then we would have to find that determinant. Well, that determinant, we could go down that row again. So it would be a22 times negative 1 to the 1 plus 1. And then we would have a33, 0, all the way down to, let me put my dots back in here. So the next one would be a43, a44, 0, all the way down to an3, an4 to ann. So you can see how the process is just going to kind of keep continuing here. So then if we wanted to find this determinant, it would be a33 times the determinant of that guy, a44, 0, an4 to ann. So then eventually what would happen, is we would get down. So we're showing a pattern here. And that's a good thing to do when you're trying to do some kind of proof. Remember, this was a33, negative 1 to the 1 plus 1, which is a positive 1. So I kind of left that piece out because we already knew it was going to be positive. So we're going to get all the way down to this last minor, which is going to have ann, n minus 1, 0, a n minus 1, n minus 1. And this would be a n minus 2 times negative 1 to the 1 plus 1. Just kind of showing that pattern. So we would get to a11, a22, a33, and get down to an2 times a positive 1 times the determinant of that 2 by 2. Eventually, you will always get down to a 2 by 2. And that determinant would be a n minus 1, n minus 1 times a n minus 0, which would just be that. That's an n minus 2. Let me clean up my notation. I'm a little crunched for room here. I'm missing an other n minus 2 here. Minus 2, n minus 2. Remember, this is the row and the column that all the stuff lives in. So you can see what's happening. Now let's throw some numbers in there, just to kind of make those ideas a little bit more concrete for us. Let's look at number 40. So in 40, we are given the matrix 5, 0, 0, 0, 6, 0, 0, 0, negative 3. And we want to find the determinant of this matrix. So I'm going to call this matrix A. Now this is a diagonal matrix, which is a special case of a triangular matrix, but that rule is going to hold regardless, and I want to show you why. So we already know what the determinant is going to be. By theorem 3.2, that determinant is going to be 5 times 6 times the negative 3. So we're going to have 30 times the negative 3, which ends up being negative 90. Now let me show you. So let's say we wanted to expand along the first row. So if we expanded along the first row, we're going to have 5 times negative 1 to the 1 plus 1 times the determinant of 6, 0, 0, negative 3. So that's going to be 5 times a positive 1 times this determinant. So it's going to be 6 times the negative 3 minus 0. So we're going to have 5, because that's what that would be, times 6 times the negative 3. So you can see how it's the entries on that main diagonal, which gives us that negative 90. Let's do another one. Let's look at 42. So this one's a 4 by 4. Now we already know what the determinant's going to be. I'm going to let this be matrix A also. It's going to be 4 times 1/2 times 3 times a negative 2. So 2 times a negative 6 gives us a negative 12. But we could do row expansions here also, and I'm going to go along that first row again. Even if you went along the last row, you would still get the same answer. Just first row is going to be easier. So if we went along the first row, and I am going to do row expansion so you can see the numbers come out. And you'll actually see this come out when we work it out. So it would be 4 times negative 1 to the 1 plus 1 times the determinant of this matrix. well, that's going to be equal to 4 times positive 1, which is 4, times that determinant. So now let's find the determinant of that matrix. So we're going to do another expansion, and I'm going to go along that row again, along that first row. So we still have the 4 hanging out. So if I go along that first row, I'm going to have 1/2 times the determinant of 3, 0, 0, negative 2. So we have 4 times 1/2 times this determinant. And that determinant is going to be 3 times negative 2 minus 0 times 0, which is 0. So we have 4 times 1/2. This number minus 0 is just going to be that number. So you can see how it's the exact same thing as what we had up here using our theorem and multiplying the entries down the main diagonal. So you can see that come out in that process. So that's a nice little shortcut for triangular matrices. It could be lower or upper triangular matrix. It could be also a diagonal matrix that will work.